Boop, 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 boop. Boop, 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 boop.
All right, Whitney. So, we have the mics.
We do.
We have you. We have me.
Right.
And
Yeah. Well, we redid the studio too, so now I can see when you're recording. So I'm not surprised anymore, because you put up this monitor right in front of my face. So
I mean, I can take the monitor away.
I could see right now that we're recording. It's great. Now there's no surprises.
I mean, this is just a test, so you don't have to worry about it.
Oh, this one's a test?
Yeah, it doesn't
Okay.
mean that it's going to go into the podcast itself.
Oh, gotcha. Okay.
You know we have to sound test first, Brittany.
You said that
Every
we never
time.
warm up anymore. We don't sound test.
We're warming up. Look, we warmed up already.
Yeah.
Did you warm up more coffee for me?
Oh my god.
I know.
What am I, an intern?
Listen, you get paid in experience.
Yeah. That's real great.
Isn't it?
Yeah. Anyway, what are we talking about today?
Science? We're talking about science, I can tell you that much.
Uh-huh.
So, we traveled to Fairbanks. Green Banks.
Green Bank.
Green
Just
Bank.
the one bank.
There's only one bank of green.
Yes, one bank. Yes, so we ended up traveling to Green Bank, West Virginia, which is in the National Radio Quiet Zone. And this is a place where radio transmissions, are heavily prohibited because there is an observatory there. So there's this huge radio astronomy observatory in this area. And that's where we traveled.
In the radio quiet zone.
Yeah.
The quietness of radios.
Uh-huh.
That's where they use like radio waves to suppress all sound in that area, right?
No, not at all. Not at all. So if you want to put up any kind of radio tower or anything, they told us that it is heavily restricted, what you can actually put up and what you can do in this area. And especially in Green Bank, there is basically no radio transmissions at all. So when you go into the air, there's no Wi-Fi, there's no cell phone service. It's totally quiet in the town. And that's so you don't get interference from these things to the radio telescopes. We want to get into the reason why we even went to this place. And initially it was because we were interested in Fermi Paradox and the Drake equation. So the Fermi Paradox is something named after a physicist known as Enrico Fermi, and it describes the paradox between the lack of evidence for intelligent life beyond Earth and the high probability of such life occurring according to the Drake equation.
Ooh, that's exciting. So, we haven't seen completely reliable evidence for intelligent life beyond Earth.
Right.
And so, these nerds, as they do, sit in a room and they scribble-scrabble onto paper and hypothesize why.
Why what?
Or why not?
Okay, that was a long pause for nothing, thanks.
Dramatic pause.
Yes. So the Fermi paradox, as said before, goes along with the Drake equation. So the Drake equation can be defined by quite a few variables. It is n equals r star times fp times ne times f1 times fi times fc times l. So that's a lot of variables, so we'll go over what each of these are. So it starts with n. N is the number of civilizations in our galaxy with which communications might be possible. And this is the variable that we're looking for. So we can adjust these different variables depending on how optimistic or pessimistic we're looking at our model. So the first variable that we're looking at is our star, and that's the average rate of star formation in our galaxy.
Okay, so what is the average rate of star formation in our galaxy?
So usually the estimates put that at about 7. It can vary depending on what model you're looking at. Some people say 1, some people say 10, some people say a little bit higher. But 7 right now, as of current estimates, is what most people are settling on.
7 what?
7 stars
Per
galaxy, formed per year.
Per year?
Yes.
You sure?
I think so.
Oh, okay.
Yeah. When we went to Green Bank too, they had that on the wall in the little tiny museum that they had. Their estimates put it at 10 stars formed per year.
Yes,
but,
their estimates did put it at 10.
Yeah, most recent estimates have put it at 7. So.
Wow.
And then another variable that we're looking at is FP. So that's the fraction of those stars that have planets. And these estimates can range all the way from 22% to 90%.
22 to 90%. 22 22 to 90.
Yes. So it's a huge range. It depends on how pessimistic or how optimistic the model is put together.
That seems so arbitrary.
Yeah, exactly. So this is just kind of a variable that can have a huge effect on the range of the number n. And then finally, following this, there is NE. And NE is the average number of planets that could potentially support life per star that has planets. So NE can range from 0.01 to 0.3.
0.01 to 0.3
Yes.
for planets that have life.
Yes, that
For-
can support life. Not necessarily have life, but can support life.
All right, so we got 20 to 90%, so to speak,
Uh-huh.
of stars that have planets.
Right.
And then of those stars that do have planets,
Yes.
only a fraction of them will have possibly habitable worlds.
Yes, exactly. So you can see how the numbers are going to drop here. In addition, there's another one, F1, the fraction of planets that can support life that actually develop life at some point. So there are planets that can support life, but that doesn't necessarily mean life will develop there.
That's true. So, how do we get life on these planets so that they can start communicating with us, so people can stop feeling lonely, even though we're completely surrounded by other animals
Yeah.
and other humans?
Yep.
What?
I'm not sure what you're talking about with that, but okay. Okay, and then there's another variable, Fi, and that's the fraction of planets with life that actually go on to develop intelligent life. So you can have life develop. For example, on Mars, there's evidence of bacteria, so life that had developed on Mars, but it wasn't intelligent life. So not only does the planet have to support life, develop life, but the life also has to be intelligent. And that's estimated to be at 0.121, depending on estimates yet again.
For it actually developing into intelligent life.
Right.
In which, in this case, we're defining intelligent life as communicatable life.
Yes. So life that has the potential to actually communicate with us, which kind of goes to the next variable, FC, and that's the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. So not only does the life have to be intelligent, they have to be able to develop this technology to communicate with
So what
us.
if they're just living off the land and didn't develop technology?
Yes. So that's another important variable because we're looking at civilizations that can actually communicate with us. Not necessarily that there's life somewhere out there. We're looking for what ones can we send transmissions to and they send them back to us. So that's the point of the Drake equation.
What happens when we get that signal back?
Who knows? Like, who knows what we'll end up doing or if it's even possible to communicate back because they're so far away from us and we're so far away from them, for example. So,
I mean, they can have all of our old TV shows.
yeah, they probably have been receiving them. At least ones that are like 50 light years away. So
Yeah.
yeah,
I can see that, yeah.
yeah. So there's one more variable in the Drake equation. That is L. That is the length of time for which such civilizations release detectable signals into space, and this is usually estimated to be about 3. So when you take all these variables together, this results in a number of civilizations in our galaxy that can communicate with us to be up to 756.
All right, so, Brittany, we put all these variables together.
Right.
We have all the little stars being formed, and the planets, and then life on them, and then intelligent life that can actually develop detectable noises, and then of those, they live long enough to actually transmit something without blowing themselves up.
Right.
And then we get some magical number
Yes.
that tells us how many there should be detectable in the universe.
The most pessimistic estimates will put this at pretty much 0 in our galaxy, and the most positive ones will put this at 756 in our galaxy. So if there are that many civilizations that can communicate with us in our galaxy, why are we not receiving any transmissions back? So that's where the Fermi Paradox comes into play. There is actually a book titled If the Universe is Teeming with Aliens, Where is Everybody by Stephen Webb. And he goes actually over 50 possible solutions to the Fermi Paradox in that book. So,
Okay.
yeah, some have been discussed by actual scientists and some have been discussed by, crazy conspiracy theorists, but we want to talk about just a couple of these because there's 50. We don't want to go over every single one.
You don't want to go over 50 solutions to the paradox, Brittany?
No, who's going to want to sit here and listen to that? So we're just going to talk about a couple of them.
Well, let's talk about the important ones at least.
Okay, yeah.
Okay. All right. So we have solutions to where people are, right? Just like at my last birthday party.
Uh-huh.
Where were people?
There was tons of people. In fact, you kept telling your roommates, "Sorry, I didn't mean for this to happen," as more people kept showing up.
Yes. It's just a joke. So that people could feel related. To me. My problem is that too many people show up.
Okay, nobody showed up to mine, so it was just you. Yeah.
You're the claptrap of our friend group.
I am the claptrap of our friend group. Yeah.
Finding other intelligent life besides yourself because you're so lonely at your birthday parties. If you wanted to make more friends,
Right.
Then, and if you wanted to make more friends, and you're looking for more intelligent life, but we haven't found it. Why haven't we?
Yes. So one of the solutions to the paradox is something known as the Interdict Scenario or the zoo scenario. So the scenario for this is that alien life intentionally avoids communication with Earth in order to keep life here to keep us safe. So, for example, this can be thought of as like a nature preserve to allow life to develop naturally, or to keep us safe from interplanetary contamination, such as diseases from their planet. So this is more of a scenario where alien life is benevolent and doesn't want to interfere in life that's happening on Earth. So that's why they choose not to communicate with us.
So alien Big Brother watching out for us, looking at us, being like, "Oh, look how cute! They have no right to be so small and cute."
Yes.
And then they just keep us from dying, except for when we're trying to destroy ourselves.
Yes, exactly. They can be perhaps observing us from afar some way, but they just don't want to interfere. So think of like going to a nature preserve, watching the animals from far away, but you don't want to interfere in what's actually happening.
But they don't know that you're there.
Yeah, they don't know that you're there. So that is one possible solution to the Fermi Paradox.
Except when you scare some of them, then they run away to their tribe and they keep trying to tell people that they saw these really weird, large bipedal creatures watching from afar, and some of them took family members and probed them. And they come back with this weird marking on their body, and then no one believes them.
Yeah.
So Gary that I met on the streets of New York, he was right.
Oh, yeah. Interesting. Okay.
Yep.
So there's other solutions as well. So another solution is known as the Planetarium Hypothesis. And this hypothesis is a little crazy, but I chose it because I liked it because it was kind of insane. But this hypothesis says that our universe is just an illusion, and we are living in an artificial universe engineered by technologically advanced life forms.
Okay, why? Why are we living in this illusion?
Okay, so some people think perhaps that a more advanced life form is using us in some way, or has harvested our resources in some way, or maybe even destroyed our planet and feels bad, so they threw us in this artificial universe and they made it so that there's no other aliens that are in this artificial universe. So it's just us kind of hooked into the matrix, and there's nothing outside because they didn't render that far.
Because they took resources from us.
Yes.
And then they plugged us into this artificial world to keep us entertained.
Yeah, it's insane. That's why I loved it. That's why I chose this one.
It sounds almost like the Matrix.
Yeah, exactly. Yeah, it's kind of exactly what the hypothesis is. Although I was reading about this one a little bit further, and the amount of memory it would take to render as far as we've seen into space would be far too much to actually build an artificial universe. So this one's kind of hokey.
Yeah, but how do you know? Right? So
Yeah.
how do you know they don't develop computing beyond the capabilities that we comprehend? A multitude system rather than a binary system, which requires those digits to be 0, 1 in order to collect the amount of information, right? So if you had a multitude, triplets perhaps, or quadruplets of different parameters that you could plug into this, the memory would be exponentially increased, capable of storing everything that you want in a nice little laptop.
Yeah, that's also totally possible. I don't think that I am living in the Matrix, but, who knows? Stop picking at your face wound.
Sorry. It's just so distracting from when you slashed me.
I'm sorry.
I'm sorry that I spoke up. It was my fault. I made you hit me. I'm sorry.
You actually did. You're like, Brittany, come here. Okay, I need you to throw me. And yeah, it's not my fault.
Don't blame me. All right, so you have the planetary hypothesis.
Planetarium hypothesis.
Planetarium.
Yes.
Like a terrarium?
Yes.
Hyperium.
A planetarium. Though.
Planetary.
Yes.
The collection of all the teriums.
Yes, essentially. So this will bring us into another theory known as the percolation theory. So the percolation theory says that it's extremely difficult to traverse the galaxy, and we know this. And in addition, materials are limited, which we also know. And as such, alien colonies will percolate or spread out in clusters instead of spread out evenly, and large areas will remain uncolonized. So it's possible that we are the only intelligent life in our certain cluster. So think of life kind of spreading out more in these big bubbles instead of like evenly. So we might be the only ones in our bubble compared to all these other little bubbles that have spread out around us. So we're nowhere nearby an intelligent civilization. That is that theory.
So like certain fungi that clump together, right? You get nice little clumps down there on the wet, moist ground. You have moss, flifflin, flufflin, right? And they're so fuzzy and cute. But you have a little patch here, then you have a patch way over there. So if we start percolating, we would develop other life near us in this small little bubble. But that bubble is detached. Detached. But that bubble is detached from other bubbles that contain intelligent life.
Right. So that's another theory. And there's a few other theories too. Really quickly, go over a couple. One is that we are perhaps the first civilization capable of communication to evolve in our galaxy. It's entirely possible. Perhaps there is intelligent life. Nobody else has developed these means to communicate.
I see.
Yeah.
So we're just the first ones in the race.
Yes. So that's one theory.
That's true. I feel like a winner. So,
Yeah.
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 I can see that.
Yeah. So there is another theory that they have not had enough time to either receive or send back radio transmissions. So we are limited by how fast radio transmissions travel, which is the speed of light, but you're still sitting around and waiting for that transmission to reach the civilization, and then they have to not only receive it, but then they also have to be able to interpret it, know where it's coming from, and send a transmission back. So that is another problem. We haven't waited long enough.
I mean, space is large.
It's huge.
Dark and deep.
Yeah.
But we have many light years to go before we sleep.
Yep. Stealing from Robert Frost, are you?
Yeah.
Okay.
Anyway.
All right. Another one is that we are not looking at or interpreting the data properly or not tuning into the right frequencies. So it's entirely possible that not only are we not looking at the correct frequency, because the radio frequency has a huge range. Think of like the frequencies that you can tune into on your car radio. There's a large range there, and it's enormous. But it's also possible that we're not actually interpreting the data correctly. Maybe we have received transmissions, but we haven't actually interpreted it the way that we should.
So they might have sent, hey, we're on our way.
Yeah.
Better be fucking pizza when I get there.
Yeah.
And we all could have saved humans from being enslaved.
Yeah.
Into pizzerias. Burning pie after pie for our overlords. If we had only listened.
If we had only listened, interpret that data properly.
Yeah.
Yep. So after that, there's also the theory that they have no desire to communicate with us.
I mean, why would they?
Yeah, like look at us. Why would they want to? So that's another theory.
Gotta be careful about the friends you keep. And if you were an alien civilization and you looked at us, would you really want to be friends with us?
Yeah, for real. I mean, we have constant war, and we're just not great to each other. We're not great to our own planet. We're not great to other life forms. It's entirely possible that they've seen kind of our violent history and decided, nah, I don't need to mess with these guys. Or maybe they're nice. They're like, oh, look how cute they are. They're trying so hard. We're not gonna communicate with them. Or maybe it's another level too, where we are pretty much like, just small insects to them. And why would you try to communicate with an insect?
With an insect, yeah.
Yeah. So there's a lot of reasons why they may not just want to even bother communicating.
So like walking into the forest and just hearing cricket, chirp, chirp, burp,
Yeah.
burp. I mean, that's basically what we do. All the insects are yelling the same things we yell, just
Yeah.
with less sounds.
Exactly. Yes. So there is another theory that they are actually just two aliens who communicate with us. So life can develop that has a completely different thought process than we do, of course. So maybe they communicate much, much, much slower. Maybe they communicate at a much higher speed. And maybe they communicate in a way that we can't even really fathom because our brains aren't wired that certain way.
Right. Posterior jigulation. Much like the humble bumblebee.
Yeah. Yeah, so maybe they communicate through dance instead of through speaking and sound. Yeah.
Yeah. We're just not dancing appropriately.
Yeah, exactly. So another theory is that we truly are alone in the galaxy. So there's actually this game called Dead Space where we are the last living creatures in the galaxy, actually the universe, because every other creature has been wiped out by this threat. So that's kind of a scary one to me, is that we truly are alone. I find that more terrifying than anything else.
That we're alone?
Yeah, that we're completely
we've been
alone.
or something has destroyed other
I
life
mean,
forms?
honestly, either one. Like, we are the only ones that have developed intelligent life on this planet. Or, everything else has been destroyed. So I find that one truly scary.
Wow, that is scary to think about.
Yes. All right, so we're going to talk a little bit about the SETI program as well. So the SETI program is known as the Search for Extraterrestrial Life. And that began shortly after the invention of the radio and has continued throughout the years. And it utilizes something known as radiotelescopy. So back to what we were talking about before, the radio telescopes. So we recently visited the National Radio Astronomy Observatory in Green Bank, West Virginia. And we got to actually speak to one of the scientists there, Ryan Lynch, about radiotelescopy, the Fermi Paradox, and a few other fun facts.
It's exciting.
Yeah.
So, let's go interview Ryan.
Yeah, we're interviewing him right now.
I mean...
Yeah, we're about to, yeah.
Right now. We have Ryan with us. Ryan, would you like to introduce yourself?
Sure. My name is Ryan Lynch, and I am a staff scientist at the Green Bank Observatory.
Wonderful.
Excellent.
And thank you for spending time with us today to talk about some of this.
Yeah, so we had a couple questions for you if you were interested in answering them. So can you explain at a layperson level how a radio telescope works?
I can. So, a radio telescope picks up electromagnetic radiation. It's fundamentally the same thing that our eyes pick up as visible light, but of much lower energy. And if we think of light as a wave, kind of a changing electric field, then the separation between the waves at radio wavelengths is much longer than at the optical wavelengths that our eyes are sensitive to. But fundamentally, it's still electromagnetic radiation, and the radio telescope works similarly to an optical telescope in a lot of ways. Radio waves from space hit a reflecting surface made of aluminum, and they get brought to a focal point, similar to the way that a parabolic optical telescope will bring light to a focal point, or a lens, like the lenses in your eyes, will bring light to a single focal point, although there they bend the light rays instead of reflecting them. Once the radio waves are brought to a focus, we are able to detect this changing electric field by measuring small changes in voltage in a little wire, which is really what the detector for a radio telescope is. And that part is different than an optical telescope or a camera, where we use an electronic device that is kind of sensitive to individual particles of light that we call photons. Once we can measure that changing electric field with the radio telescope, we are able to measure the power at different radio wavelengths or radio frequencies. That's the way we usually think about it. And we can look for particularly strong emission at certain frequencies that are given off by individual molecules in space, or we can look over a wide range of frequencies at objects that give off radio waves over a very wide range of frequencies. And using that technique, we can study objects and phenomena that we wouldn't be able to see any other way, because they only emit at radio wavelengths. They don't emit at optical wavelengths or X-rays or gamma rays. So it really gives us a much more complete picture picture of the universe when we can study it using all of the electromagnetic spectrum.
Excellent. So that actually leads into the second question I was going to ask. What celestial bodies or phenomena do you actually use these radio telescopes for? And what purpose is there behind that?
So it's a really wide-ranging and diverse set of science that you can do in radio astronomy. The thing that I work on particularly the most are called pulsars. These are dead stars, and they emit radio waves in a beam, kind of like a lighthouse beam, and they also spin really, really quickly. They can spin up to hundreds of times a second, so very, very fast. And anytime that lighthouse beam points at our telescope, we see a little pulse of radio waves, hence the name, pulsars.
Huh.
And these actually can act like clocks in space because the rotation is very, very regular, and each pulse can act kind of like the tick of a clock. And if we see minor deviations in the way that that clock appears to be ticking, we can use that to study the physical environment of the pulsars or things that are impacting the signal as it travels to the Earth. And because they're such precise clocks, and because they're such extreme objects, they're close to becoming black holes, their gravity is so strong, we can use them to study a wide range of really interesting and extreme physics. So that's the kind of thing that I get the most excited about. But you can use radio astronomy to study a wide variety of other stuff. Radio astronomy is great for studying very distant, powerful galaxies and the supermassive black holes at the center of those galaxies called quasars. We can use radio waves to study hydrogen in the universe, and hydrogen is the most abundant in the hydrogen is the most abundant element in the entire universe. So it's what most of the normal matter in the universe is made out of, and we're able to study most of it using radio astronomy because it emits at a very particular frequency. We can study the regions where stars are born. We can study regions where new planets are being formed. We can study comets and asteroids and other bodies in our solar system. We can study the universe on the grandest scales, cosmology, the study of the history and the evolution and ultimate fate of the universe. So radio astronomy really runs the gamut of all different types of astronomy, and there's plenty of other things I didn't even mention.
Wow. So because you can study so many different various things with radio telescopy, is there any advantage of optical telescopes over radio telescopes?
Well, I would say that all different types of telescopes are very complementary to each other, because whenever you look at different energies, different forms of electromagnetic radiation, you are going to probably see different types of objects and different phenomena that you wouldn't be able to pick up otherwise. We would have a really incomplete view of the universe if we only limited ourselves to studying astronomy at one particular wavelength. Optical astronomy was the only game in town for a long time because we didn't know how to build radio telescopes. We didn't really even know about radio waves up until relatively recently. Same thing with X-rays, gamma rays. And so we studied a lot of stars, planets, and did great astronomy at optical wavelengths for a long time and continue to do fantastic astronomy. But we didn't know about pulsars. We never would have known about most pulsars if we couldn't study them with radio waves. And so all of these different types of instruments and tools give us a much more complete scientific picture of the universe around us. And what's really exciting at this particular era in astronomy is that we're not just now limited to using light, electromagnetic radiation. In just the past few years, we started to actually use gravity to study the universe as well. These are called gravitational waves, and we can actually use, we don't always think of them as telescopes, but they really are kind of gravitational wave telescopes, or gravitational wave observatories, to study the universe with gravitational waves, which is fundamentally different and gives us a picture on black holes and neutron stars and very, very massive objects like that. And one of the things that's cool is you can actually use radio astronomy to study gravitational waves as well. There's a project that we're doing here at the Green Bank telescope. It's also being done with a lot of other radio telescopes around the world to try and directly detect gravitational waves using those objects, pulsars that I talked about.
Wow, that's really cool. So we were originally in our episode delving into talking set SETI, and I was specifically told we can't ask questions about it, but I can ask you this. What are your personal thoughts as a scientist on the Fermi Paradox?
Yeah, so I think that there's just a lot of unknowns, and so a lot of it comes down to kind of an intuition, maybe an educated guess, but also just opinions on some of the terms. I mean, one of the most important in the Drake equation which kind of governs the expected number of civilizations that we might expect to find in our galaxy at any given time, is how long a civilization actually lasts, or at least tries to communicate. You can envision a civilization advancing past the point where, however they communicate with each other, is a way that we wouldn't be able to pick up. And from our perspective, in trying to detect them, it's kind of the same thing as if they were just go extinct or something. Mm-hmm. And I give talks on SETI to visitors at the observatory from time to time. And I always like to ask people, when I get to that term in the Drake equation, the lifetime of a civilization, what people think about it. And I find that I'm way more optimistic than most people about the fate of humanity. Because I kind of think that, I think we'll probably be around for an indefinite period of time. I have a lot of faith in our ability to innovate and adapt to whatever challenges might come around. Most people are a little bit more pessimistic and maybe a few thousand years, maybe a few hundred years. I had one guy who was like, no, we're like done in like 20 years. And I was like, I hope you're not saving too much for retirement if you really believe that. So I think because of that, I tend to be pretty optimistic about the odds of intelligent civilizations being out there, and perhaps even being able to detect and even communicate with them at some point. Mm-hmm. But I have to admit that that's really just speculation on my part. Mm-hmm. And I think there's a lot that we don't understand about how intelligence emerged on Earth and in human beings to really be able to say whether or not that would be common. I suspect that life itself is probably common, but that doesn't necessarily mean intelligence is. But the only way that we're ever going to be able to actually definitively answer that question, or at least build confidence in one of the potential answers, is if we go out and look for it. And so I think that that's one of the great things about SETI.
Mm-hmm. So do you think with all the time and effort put into finding these things, are you more likely to find intelligent feedback since we keep propagating and trying to look further and further, or would you more likely find life but not necessarily intelligent?
Well, I think that probably depends on how you're looking. Some of the future telescopes that are being planned for the next few decades will have a decent chance of finding at least very strong circumstantial evidence for life around some perhaps nearby stars. They'll do this by being able to actually see the atmospheres of planets orbiting those stars, and perhaps looking for molecules, elements in the atmospheres that you wouldn't expect to find unless there was life. Oxygen is a great example. There's a lot of oxygen in Earth's atmosphere, but that's because plants make it. If plants were not renewing the oxygen in their atmosphere, it would get absorbed or react with rock and other material pretty quickly. On a time scale, I'm not actually sure exactly what the time scale is, but on a cosmic time scale, it's really fast. And so if you see a lot of oxygen in the atmosphere of a distant planet, it doesn't guarantee that there's life there, but it would be pretty strong evidence that something like a biological process is replenishing the oxygen. And so you can imagine other what are called biomarkers like that. I mean, it's even possible that we could find life in our solar system, perhaps like around one of the moons of Jupiter or Saturn. With radio astronomy, I think that there you're probably more likely to detect a technological signature, which would actually then be a sign of intelligence, as opposed to just a biological signature, which may or may not be a sign of intelligence, but would be a sign of life, perhaps. So both of those techniques are really complementary, and it kind of depends on what you're trying to find. Either detection, I mean, obviously intelligence, but any kind of detection of life would, I think, just be a game changer for our understanding of the universe around us and kind of our place in it in a more philosophical sense.
Oh, yeah.
Wow. All right, absolutely. So one of the main points of our podcast, one of the main, what's the word?
Mission statement?
Mission statement. Mm-hmm. Our mission statement of our podcast is to not only educate people in a fun way, but also combat some misconceptions that may occur in the public interest as far as science goes. So what kinds of misconceptions have you come across about your particular field of work that are really common?
One of, I think, the biggest misunderstandings that people have about radio astronomy is that we're listening, like physically with headphones or something like that, to sound. And that's because when we interact with radios in our everyday life, we usually interact with maybe like a car radio, or, I mean, now we call podcasts radio still yet, even though we're not picking up over the air radio, although your Wi-Fi is still using radio frequencies to communicate to, so that is a form of radio. But I think a lot of people associate it directly with sound. And you certainly can take radio waves and convert them into sound because you can encode information in them and turn it back into sound. We could, in principle, with some of the equipment that we have, plug a speaker in. It would just sound like static most of the time, though. And radio astronomers are never actually sitting there with headphones on listening for a signal. There was a movie, Contact, with Jodie Foster back in the 90s. So every radio astronomer has seen this, and I think probably a lot of audience members, at least of a certain age, will have seen this. And there's a really iconic scene of her like sitting in the desert next to the Very Large Array in New Mexico. It's a collection of a number of radio telescopes out there that are tied together to be used as one instrument. And she's got some headphones on. She like hears a SETI signal. And it's very romantic, and it makes for a great shot, but that's not how we're actually doing it. We're recording data digitally and analyzing everything on computers, sitting in offices, just like most people probably are. So that would be one thing. Another, I don't know if it's a misconception, but maybe something that people don't necessarily appreciate is just how ubiquitous the use of radio frequencies are in our everyday life and with technology. Bluetooth, Wi-Fi, cell phones, the collision avoidance radars are becoming really, really popular on cars, airport radar, weather radar, your cell phones, gas-powered vehicles, spark plugs in gas-powered vehicles, electric power lines, which could include like electric fences, electric blankets, microwave ovens. All of these things, and way more, give off radiation at radio frequencies. And radio telescopes have to be really, really sensitive because the radio waves that come from space are really, really faint. And the man-made or human-made radiation, the human-made radio waves are, by comparison, very, very strong. And so that's why you guys came to West Virginia in the middle of Pocahontas County here in the mountains in what's known as the National Radio Quiet Zone. This is actually a protected area where the use of radio transmissions is limited so that it doesn't interfere with the operations of the Green Bank telescope. It's a really important resource for us. And so we have a lot of visitors who will come here, and we ask them to turn their cell phones off and to place their Fitbits or their Apple Watches inside a metal box if they go down by the telescope, because these things are just all around us and we don't even necessarily realize it, but we're acutely aware of it in radio astronomy. It's the equivalent of light pollution for a radio astronomer, and it's something that has tremendous benefits. I mean, all technologies that we use have tremendous benefits, but it also poses a real big challenge for doing radio astronomy.
Right.
Wow. So the sensitivity required to do your research, because you have such faint waves, I was told that your telescopes are capable of picking up the radiation from our microwave opening, the little bit coming out, and being detected from that.
Oh, absolutely. In fact, there's an interesting story I'll relay about that. So there are these mysterious phenomena that we are observing with radio telescopes now called fast radio bursts. And the name basically describes what they are as far as we know. They are very short, few millisecond long pulses of radio waves that sometimes seem to repeat from the same location on the sky, but sometimes appear to be one-off events. And we know that they're coming from very distant galaxies. The first one was very strong. It was very unexpected. And there was a little bit of question about whether or not this was a real astrophysical signal or whether or not it was some sort of human-made terrestrial signal. And then a few others started to be detected, but they were a little bit weird in the way that they behaved with time, the kind of the distribution of energy at different radio frequencies. And they also, it was eventually realized, were occurring around the same solar time each day. And that's not what you would expect for something coming from space. You wouldn't expect there to be a direct relationship to the time of day according to the sun. Since then, we've now discovered a number of other of these fast radio bursts that are very, very clearly coming from space. They're definitely astrophysical sources, although we don't know what's causing them. But this kind of class that was found for a little while there, the ones that seemed a bit strange, that were kind of tracking solar time, it eventually was learned that these were being given off by an improperly shielded microwave near a particular radio telescope. And when the door was opened, the changing size of the cavity that the microwaves were bouncing around and caused the frequency that they were peaking at to change. And that's why you had this particular structure to the signal. Because they're also only being detected at like one radio telescope, which is also a bit weird. And people realized that these were probably not astronomical, but there was some question about whether it was some sort of a local atmospheric phenomenon. It's like, no, it was a microwave. So here in Green Bank, all the microwaves on site are shielded in metal boxes, and you actually can't turn them on unless the box is closed, and it keeps all of the microwaves trapped inside.
That's funny. So finally, we have one last question.
Sure.
Do you have any fun astronomical facts for us?
Oh my goodness.
I know you
So
probably
many
have
facts.
a lot.
But I keep talking about pulsars because that's what I study.
Yeah.
And that's what I'm kind of very excited about. So I'll give you a few fun facts about pulsars. Pulsars, like I said, are dead stars. They form basically from the remains of a supernova explosion. When a star ends its life, a massive star ends its life, it explodes in a supernova, but not everything necessarily explodes, and there can be a very dense core left behind. And that core is made mostly of neutrons, kind of one of the subatomic particles that we find at the centers of atoms. And it's extremely dense. It can weigh 500,000 Earth masses, 500,000 times the mass of the Earth. But all of that material is crammed into something which is only about 20 kilometers in radius, or diameter, or so.
Wow.
The equivalent density is the same as taking all 7 billion people on the planet and squeezing them into the size of a sugar cube. Now, as you can imagine, we wouldn't remain human beings at that point. We would be something else, but we don't exactly know what, because we don't actually know how matter behaves at those densities. And so neutron stars and pulsars can be a way of probing subatomic physics at those scales that we otherwise couldn't do. They're also very strongly magnetized, and the magnetic fields are so strong that if you were to place one of these pulsars at the distance of the moon, it would wipe out all the credit cards and spinning disk hard drives on Earth. The gravity would also destroy the planet, so we would have other things to worry about. So these are things that we can't create in the lab, and luckily, it's good for us. We don't want to destroy the planet. But luckily, we can study them using radio astronomy. Nature has given us a very nice natural laboratory for studying extreme physics in those ways. So very cool, very deadly. It's good that they are several thousand light years away from us.
So pulsars, dead suns.
Yeah, basically. Yeah.
Okay. All right.
Yep.
Cool. They just explode, and then you have a tiny little collection of dense matter left over.
That's the basic picture, yeah.
Oh yeah. Oh, just making sure that there's a base picture.
Yeah,
Right.
and like I said, they also spin really quick. So the fastest spinning one spins 716 times per second. That's the fastest we know about anyway. There could be ones that spin faster
Right.
that we haven't found yet. So imagine a city-sized atomic nucleus spinning as fast or faster than a kitchen blender. And
Okay.
that gives you some sense about what a pulsar is like.
Wow. and as like a nice scene, you just observe these for a long period of time and collect data and then do whatever your analysis is, right?
Yeah, these, to us, they just kind of look like little blinking point sources. And so we collect data on them. And most of the analysis that we do is in trying to understand, like I said, there's very minor changes in when the pulses are arriving at our telescope due to whatever physical phenomena might happen to be impacting it. And so that's how we're then able to do this really great and extreme physics.
Man. How many do you study at once?
Well, at any given time, we're usually only observing one at a time, because they're kind of spread around. Although there are some objects in the galaxy called globular clusters. These are dense collections of lots and lots of stars that also contain lots of pulsars. And so we can study several dozen sometimes at a time when we're observing them in globular clusters. We would really like to detect some very close to the center of our galaxy, because that would allow us to study the black hole at the center of our galaxy. So that's a big goal, but not one that we've actually been able to achieve yet. But there are about 2,500 pulsars known total.
Man, that is a crazy and amazing fact.
Yeah, that's a good fun fact. That's a very fun fact. Well, Joel, do you have any more follow-up questions, or?
No. I think we've taken up some time and learned a lot of really cool radios, telescopy, sciencey things.
Excellent.
Yeah. Thank you so much for your time, Ryan. We appreciate it.
Yeah, you're very welcome. Thank you.
Thank you. Wow, Brittany. Wow, Brittany. Wow, Brittany. Wow. Okay, I just need to get my energy levels up.
Okay.
All right. Wow, Brittany, that was so cool.
Oh.
Wow, Brittany, that was cool. Whoa, dude.
Okay.
Space is like totally far out,
Oh
man.
my god.
So, we went and talked to Ryan at Green Bank.
Yes.
The one bank.
Yeah. Just the one bank. Yes. Not.
Man, that was exciting. His work on pulsars,
Yeah.
phenomenal work.
Very interesting stuff. So, not really related to the Fermi Paradox, but I'm very glad I got to learn about pulsars because they were really, really cool.
And just to note, we weren't allowed to talk about the search for extraterrestrial life.
Yes,
We were specifically told we couldn't ask about it.
Yes, exactly.
Which means there's something there.
Yeah, they're hiding something. They're hiding something from us. Yeah. But they let us into the facility and everything.
It was a great facility, very wonderful people. I highly recommend, if you have the capabilities of visiting there, to go see the laboratories and the radio dishy pishes.
The telescope.
The telescopes, yes.
Yes.
Radioscopes.
Yes. So.
Radiology.
Yeah. So there's multiple telescopes there too. There's some smaller ones, but the cool one is the giant radio telescope. So that's the Robert C. Byrd Green Bank telescope. This thing is huge. Like, you've almost lost your mind seeing it from the bottom, like up close.
It was intense.
Yeah. I've seen it once before, so I was just like, oh yeah, I've seen it before. But you were so excited.
So this massive telescope, which is built out of metal, out in the open, where it rains and you have all the corrosion, right?
Yep.
So talking with Aaron, who very joyously took us around and told us about the telescopes.
Yes.
Upon learning that it was built to last 50 years, I asked what they do to retire it, and he's like, they just keep running it until it literally falls down.
Yeah.
So...
Yeah, I thought that was funny because this thing is huge. So what happens if you're just like standing next to it, and
Yep.
there
it goes.
Yeah. All right.
Yeah.
Well.
Well, it only happened once.
Yeah, there was a telescope that collapsed, and there's somebody that was working in the building nearby when it collapsed, and they were okay, luckily. But it was also quite a large telescope. You do not want this to fall on you.
Oh yeah. So that was fascinating. I'm glad we got to learn about that. Brittany.
Yes.
And I feel great. Is there anything else you want to add to Pulsar's SETI program, Fermi Paradox, finding other intelligent life?
No, I don't think so. I think that kind of wraps it up. We had a great interview, a great trip to Green Bank, and it was a lot of fun.
Yeah. And so if you liked what we've done and traveling around and talking to more experts, which we plan on doing, you can always visit us on any of our websites, talk to us through any medias, give us money so that we can continue to produce some more quality for you guys. All of these things can be done, Brittany.
They can. So you can go on our social media. We're on Facebook, Instagram, Twitter under PRT Cast. Our Patreon is under PRT Cast. Nobody's donated anything yet, but I'll keep asking. We also recently started a travel blog to talk about our documentation of going to these places. So I have posted the link on our social media as well.
Have we talked about bioluminescence?
Not exactly. We talked about it in our first episode a little bit.
Have we talked about the wave after wave of men that you have to send outside of the castle as the proper defense strategy?
We absolutely have not. But I will go over that in the travel blog because the next post in the travel blog is about our trip to Florida. So
awesome. Well, guys,
Yep.
Tune into this and that and everything else.
Yep.
Thanks for listening to us again this week.
Yeah.
Always appreciate you loyal, dedicated fans.
Yes, we do. Thank you very much.
Yay.
Yay.
All right. We will see you next week.
See you next week.